Alrighty, welcome to Chemical Calculations, Chapter 9. By the time we finish this lecture and you get just more comfortable with this content, I hope that you can look at this chart and think like, okay, this chart is like really helpful. So basically this chart is telling you everything we're going to talk about in this lecture. So everything about chemical calculations is essentially going from, mass to moles to moles to mass to particles. And that's going to make a whole lot more sense by the end of this chapter. But I do think that this chart is just really helpful. So, by the end of this lecture, you can always come back to this chart and just look it over and see like, oh, okay, like this is kind of the summary of everything we talked about. All right, the first thing we are going to talk about is the mole. And the mole is this tiny little creature that lives underground, that's blind, that hunts and eats earthworms. And if you can make the sound of a mole digging on a tree using a saw, they found that you can actually make earthworms like explode out of the ground because they're all basically doing a sprint up to escape from the mole. And then you can collect earthworms. Fun fact. That has nothing to do with what we're talking about, but a biology fact is always a fun fact. In chemistry, the mole is a number. Specifically, it is 602 hexillion, which totally sounds like a number your little sister just like made up. But it's not. It's just really, 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 really big. So if we were to try to imagine it, a mole of basketballs would be 602 hexillion basketballs, and that would be enough basketballs to form an entire planet, like with just basketballs. It's massive. And so we don't actually write that number out with like all those zeros. We put it in scientific notation. And so in scientific notation, it's going to be 6.022 times 10 to the 23rd. And you are going to need to know this number. This number is going to be important. And so it's a unit of measure that just makes counting atoms practical. So if you're talking about large objects like donuts, you say, oh, there's a dozen donuts. And it's like, okay, that's 12 donuts. If you're talking about, oh, there's a mole of carbon, you're like, oh, that's 602 hexillion atoms of carbon. But if you see right here, this is showing kind of what a mole of carbon could look like on a little scale. And so this is just really fantastic because atoms are, beyond microscopic. Like we can't see them. They're so tiny. And so this makes working with atoms a lot more doable because there's no way we could count atoms. One, we can't even see them. Two, there's just like too many of them. So Avogadro's number is going to be just really important for this conversion right here. Atoms or molecules to moles. So if you were given a problem that says, hey, I have this many moles of, sodium, how many atoms do I have of sodium? Or I was given this many atoms of sodium chloride, how many moles do I have? And so you can use Avogadro's number to convert between the two. So we are going to do a practice problem with that. Before we jump into the weeds with doing chemical calculations, you need to understand how to report your final answer. So your final answer needs to be reported using significant figures. And so what a significant figure is it's a measure of accuracy. So it's saying like, okay, if I have like NASA's like super epic, awesome scale, and I could measure to like the, all the way to like the 20th decimal point with extreme accuracy, it's like, great, then I can report that number. And then I'm also using a scale, like a scale that I use at home, just to like measure, my vegetables. And it can report up to like the second decimal place with accuracy. It's like, okay, if you're doing calculations with both of those numbers, like your final answer has to be to your least accurate number given, meaning like the smallest number of significant figures that was given is how you're going to report your answer. And that's because if you were to, use both scales, say like 6.02 times 1.349874321, whatever. And then you were to say that equals, and you were to give this answer that has all these decimal points. It's like, well, you don't actually know for that first number that you got what numbers came after that 6.02. Like, you don't know all those other numbers. And if you report an answer that's like highly, highly specific, it's kind of like saying like, oh, yeah, I am 100% sure that this is what it is. But if you were to measure that same thing that you measured on your little vegetable scale and you use NASA's super specific scale, you might have a totally different number because you get all those trailing numbers. So all I have to say is significant figures, these are just the rules for counting significant digits. So how do you know what is significant and what's not? So number one, all non-zero digits and any zeros containing different non-zero digits count. So basically 300,042 has 6 significant digits. We're going to count all these zeros because they're part of the number. Whereas if you have 0.000034, these first leading zeros, they're not going to count as significant digits. However, if you have these trailing digits, these trailing zeros after the decimal point, those are going to count as significant digits. And trailing zeros, even if it doesn't follow the decimal point, again, they're not typically going to count as significant digits. So you can go with your most conservative, like, oh, I'm just going to say this has 2 significant digits. So yeah, this again, it's all about reporting accuracy. So when you report it, it's like, how sure are you that this number is accurate? You're like, okay, well, I can report up to 2 significant digits. And that's how I know for sure that these numbers are accurate. Anything that comes after that, I don't really know how accurate that is. This is going to be our first of many practice problems, and it is going to be practicing using Avogadro's number converting between moles and atoms. Now, if you notice that the background has kind of changed, it's because this problem was re-recorded several hours after the rest of this PowerPoint was recorded, after I'd already uploaded it to YouTube, and realized, gasp, I made a really dumb math mistake. And I was like, I gotta take that off. So this is the only slide that is gonna be a little bit like what is happening in this slide? So we have the problem to be set up. And sorry, before you set up your problem, announcement, get a calculator and make sure you have your periodic table. Your calculator needs to have the ability to write in scientific notation. So it can be a scientific calculator, it can be a graphing calculator, and it could be your phone calculator, as long as you are able to turn your phone sideways and use parentheses and exponents. So now that you have everything you need, we are going to read our problem and set it up. So how many atoms are in a 0.256 mole sample of iron? So every time you set up a problem, you are going to start with what you do not know. So basically, what is the question? I'll try to make sure you can see it. What are you trying to find? You are trying to find your atoms of iron. Now, what do we know? Well, we know that there is 0.256 moles of iron, and we also know Avogadro's number, 6.022 times 10 to the 23rd. And you're like, how do I know that? And it's like, because you memorize it, because you think about it day and night. Because when you think about chemistry and you think about the amount of hours you want to spend on chemistry, you're like, oh man, I wish it could be like 6.022 times 10 to the 23rd. Or maybe that's how much you don't care about chemistry. It's a personal matter. So now that we have everything written out, what we know and what we don't know, when we write out our equation to try to convert between moles to atoms, we're going to always start with what we know. So I need to make sure I'm writing this so you can really see. All right. So we know we have 0.256 moles of Fe. And what we are trying to do is we're trying to get to atoms of Fe. So that means we need to write mole of Fe on the bottom. And why I know I need to write Fe, mole of Fe on the bottom and atoms of Fe on the top is because you do not want to report this answer in moles. You want to report it in atoms. So your top unit is going to cancel out with your bottom unit. And that is just the nature of how ratios work. And so, guys, I cannot overemphasize enough how essential it's going to be for you to write out all of your units of measure. So your moles of Fe, your atoms of Fe. If you lose your unit, if you don't write your units, that's like losing your phone. It's like, for those of you who don't have a phone, it's like your parent losing their phone. It's like that's your everything, like your credit card information, your banking, your maps, your contacts, your cat memes, like all of that is lost. And so like so much of life is lost. And the same thing is true here. If you lose track of these units of measure, you are going to get lost in the sauce. Like the units of measure are really what's going to set up the whole equation. And from there, you could just write in your numbers after you've wrote in your units of measure. So we're going to have moles on the bottom, atoms on the top. And so we know for every 1 mole of iron, we have Avogadro's number. We have 6.022 times 10 to the 23rd atoms of iron. So basically you're saying, if we were to give an example, it's like, oh, for every dozen donuts I have, which I would write dozen donuts on the bottom, on the top I would write that equals 12 donuts. So it's just telling you like the exact same thing. A 1 mole is equal to 6.022 times 10 to the 23rd. All right, now that is set up, you are just going to solve. And so you're going to use your handy dandy calculator. And I'm only going to show you this one time using your calculator, how to input Avogadro's number on your calculator. So I'm going to turn my phone sideways, and I type in 6.022, and that's going to be, you use your E button, so that big capital E button right there, that is going to stand for times 10 raised to, and then you put your power, so 23. And see right here, it shows you, yep, that's Avogadro's number. And now I'm going to look at my equation and say, okay, what am I multiplying Avogadro's number by? Oh, I'm multiplying it by that 0.256 moles. So I multiply that by 0.256. And your answer is going to look probably like this, or something very similar. So the question is, how many digits do we write for our answer? So you're going to look at your significant figures that they gave you for the known, which is 1, 2, 3. You have 3 significant figures for your known because that 0 before the decimal doesn't count. And you're going to report your answer to 3 significant figures. So that's 1.54 times 10 to the 23rd. And then make sure, again, you write down your units of measure. So that's atoms of Fe. So how many atoms are in a 0.256 mole sample of iron? There is 1.54 times 10 to the 23rd atoms in that sample. And that is how you solve your first problem. Molar mass is going to be really helpful to understand, because just as we just practice converting between atoms or particles and moles, we can also convert between moles and grams. Like which is extremely useful because in lab, what you're measuring most of the time is the grams of something, like its weight. You can put a substance on a scale and measure that out, and then you can convert to understand exactly how many atoms you're dealing with or how many moles you have. So the molar mass is an extremely important conversion factor to be able to use. And the molar mass is just the equivalent to the atomic mass of the element. So your molar mass is going to be reported on your periodic table. Like your periodic table is just the most brilliant scientific tool ever invented ever. And that's coming from someone who doesn't even like chemistry is like not my bread and butter, but man, do I respect the periodic table. It really just has it all. And so this has been experimentally proven. They have found that 1 gram of hydrogen, this 1.007 grams of hydrogen is going to equal 6.022 times 10 to the 23rd. Again, there's that number, that magic, beautiful number that you should have like imprinted in your brain. And so, like I said, this will be important to understand for our problems when we're trying to understand, like, okay, if we have this many moles of element or of a compound, how many grams would that be? Or vice versa. For this practice problem and probably the rest of the practice problems, you have your calculator. You also need to have your best friend with you, your periodic table of elements. So this practice problem is going to be going from moles to grams. So that should make you think, okay, if I'm going from moles to grams, I'm going to need to be using my molar mass as a conversion unit. So what is the mass in grams of 6.58 moles of iron? We're going to set up our problem, and we're going to first designate what do we not know? What is our unknown? So what are we trying to find? We're trying to find our grams of iron. What do we know? So what we know is that we have 6.58 moles of iron, and we can find out our molar mass of iron, just like in our last practice problem, we know Avogadro's number. So the molar mass of iron, check out, consult your best friend. Iron, it says it's 55.845 grams. That is going to be your molar mass. It's also your atomic mass. It's just like a very convenient number. You don't have to do anything with that number. So now we are going to write out our problem starting with our known. So again, let's just start with writing out our units. So we know we have a certain number of moles of iron, and we're trying to get to grams of iron. So we want to cancel out this unit. If we want to cancel it out, that means it has to be on the bottom. That is how you cancel out units. The top and the bottom are going to cancel out. So we need moles of Fe over here. And what we're trying to get to is our grams. Grams of iron. Okay, so now that we've written out our units and we know this is going to get us to the unit we want, it's going to get us to grams of iron, we can go in and we can fill in our numbers. So how many moles of iron we have? We have 6.58 moles of iron. And then how many grams of iron do we have? Well, we know that the molar mass is 55.845 grams of iron over 1 mole, which means, in layman's terms, for every 1 mole of iron, if you were to weigh out 1 mole of iron, you would have 55.845 grams of iron. And they just figured that out. And that's why it's reported like that on your periodic table. So now what you can do is you can use your calculator and you can solve for this problem. So you should kind of pause, solve for the problem, and that should give you, once we cross out those and we multiply it straight across, we divide it by the 1, is 367 point, let's see here, I'll just write it out, 46 grams of iron. Now, you have to report your answer using significant figures. And so with your significant figures, you're going to say, okay, well, they gave me 3 significant figures. 6.58 has 3 significant figures. So my final answer has to be reported with 3 significant figures. So that's 367. It's a 4, so we don't round up. We don't change this number at all. So we'd say 367 grams of iron as your answer for your question. So the first 2 practice problems we did, we went our mole to how many atoms, the number of particles that were in iron. And then our second practice problem we did is we went from mole, we went to the left, we went how much mass is that? How many grams is in that many moles of iron? And so your mass to moles to particles conversions, our moles are always the bridge between your mass and your particles. So basically it's saying, if I say I have, this many grams, I have 5 grams of boron, how many particles is that? I would then convert going over through moles to get to particles. So we are going to do, again, a practice problem. So this is going to be our first practice problem that requires a 2-step process to get to where we're trying to go. So how many krypton atoms are in 3.87 grams of krypton? So we are starting with known, we're starting with our grams, and we're wanting to move to our particles, to our number of atoms. So as always, we are going to start by writing out do you not know? What are you looking for? So you're looking for your atoms of krypton. What do we know? Well, we know that there's 3.87 grams of krypton present. And we know the molar mass. And we know we need to find molar mass because we're starting with grams. And the molar mass is going to serve as our conversion unit to get us over to moles. So we know that for every 1 mole of krypton, it's 83.798 grams of krypton. And we know that because I just looked up on my periodic table. I looked at that little tiny number that's under krypton and wrote that down. And then Avogadro's number is going to be that conversion factor we need to get over to the number of atoms. So once we get to our moles, we'll say, okay, for every 1 mole, there's 6.022 times 10 to the 23rd atoms of krypton. So now that we have written everything that we know out, we are going to start by writing out our equation, but we are not going to use any numbers. We're just going to use our units. Your units are going to lead you to the correct way to write this out. So we're going to start with what we know. We know grams. We'll start with grams of krypton. Okay. For our grams of krypton, we know we need to cancel out the grams of krypton because we're not looking for grams, we're looking for atoms. So grams of krypton is going to go on the bottom. That way the 2 will cancel out. And so the grams of krypton, there is, for the molar mass of grams of krypton, there is 1 mole of it. So the mole goes on top because it's gram per mole. And then again, we don't want moles, we want atoms. So we need to take, if you look at this little flow chart right here, we need to take that next step and we need to say, okay, I need to cancel out, moles of krypton. I need to cancel out the moles of krypton and I need to convert it to my atoms of krypton. And if you're confused, you can also just look at this flow chart. But all this is saying is you have a certain amount of grams of krypton per every 1 mole. You have a certain number of atoms of krypton per 1 mole. So we are going to write in our numbers. So let's start with what we have. We have 3.87 grams of krypton. And the molar mass for every 1 mole of krypton, there is 83.798 grams of krypton. And then for every 1 mole of krypton again, because we're just saying like this is an equivalent number here, the atoms, there is Avogadro's number, 6.022 times 10 to the 23rd atoms of krypton. And now that you have those written out, you are going to solve them using your calculator. So now that you've calculated your answer, you will get to 2.78, oh man, sorry, that does not work, 2.78 atoms of iron. And you know that that's right because you're able to cross out your units as you went. Grams of krypton, those cancel out. Moles of krypton cancel out, and that's left with atoms of krypton. So you know that this is the answer you're looking for. So we're gonna, up to this point, we just talked about single elements. So now we're gonna talk about compounds and the compounds and how they relate to the mole. So your compounds is something that contains 2 or more bonded atoms that behave as one unit. For example, CO2, H2O, NaCl, table salt, water, carbon dioxide. Those are all compounds. So to find the molar mass of a compound, you just add the masses of the atoms contained in the compound. And so this will be expressed as grams per mole. So we have CO2 is your example. And if you're saying like, okay, what is your molar mass of CO2? All you do is you look up carbon on your periodic table, and that's 12.01, and then you say, okay, well, on our periodic table it's not quite that, but we have just a few more, one more number of accuracy, but on this example we'll use this. Oxygen has 16.00. For this example, on our periodic table it says 15.999, but for this they said 16.00 plus 16.00. And so once they got these 3 written out, they just added them together. And let's see, let me erase these so you can see it. They added them together down here. So they said the molar mass of carbon dioxide is going to be carbon plus oxygen's molar mass, or their atomic masses. So they're, those are equivalent things, and that is recorded on your periodic table. And so the sum total of your molar mass for carbon dioxide is 44.01 grams per mole. Now, this is very simple to do, but it just means it's a little more annoying when you're doing practice problems because it's just some extra steps you're going to have to take to find the molar mass of a compound. It's nothing bad, just make sure you have a lot of space to write. Now we're going to talk about chemical formulas. So there are multiple ways to write a chemical formula. You can write a chemical formula using its structural formula right here. And so what a structural formula is it's actually showing you where the atoms are in the molecule and how they are bonded to one another. So we actually did a lot of structural formulas in a previous chapter, and they're really helpful, but they're also like extremely cumbersome, and it'd be really annoying to have to write out a structural formula like every single time you're just trying to write something out. So other ways of writing a chemical equation is using its molecular formula. So the molecular formula is going to tell you exactly how many atoms are in this compound. So there are 4 carbon and there are 10 hydrogen. So we see that down here in the structural formula. This is showing you exactly how they're bonded together. And the molecular formula is telling you just a shortened okay, well, instead of showing you this whole long structure, we're just going to tell you this is what it is. You have 4 carbons and 10 hydrogen. And then the empirical formula actually takes your molecular formula and it simplifies it. It's saying, okay, could we simplify this down? Yeah, we could divide this molecular formula here. We could divide it by 2. Kind of right over that. We can divide it by 2, and then we could get a simplified version. So it's the simplest whole number ratio. So this empirical formula for C4H10 would be C2H5. And we are actually going to do practice problems figuring out the empirical formulas based on the masses that we know and the moles that we know. So we're really going to kind of focus in on the empirical formula. So again, just like I showed you in that last slide, this slide is just showing you take your molecular formula, which has all of the atoms present, and you divide out to make it your smallest whole number ratio. So C2H4, its empirical formula would be CH2. The percent composition is just saying it describes the mass composition of a compound by showing what percentage of its total mass comes from each element. So in layman terms, I really like this example. It has a bracelet. And this bracelet, if you have your Taylor Swift Best Friends Forever bracelets that are all the rage, this bracelet is going to have different colored beads on it. And so if you were to try to find the percent composition of the pink beads on your bracelet, what you would first do is you would count all of your pink beads. So there's 3, 6, 9. So there's 9 pink beads. And you would say, okay, well, if I have 9 pink beads and I have a total of 20 beads on my bracelet, the percent composition is going to be 9 divided by my total, which is 20, times 100%. So your answer would be 45% of my bracelet is made up of pink beads. And you could do this for all your other colors. So in the same way, you can do percent compositions of compounds. So H2O, C2H4, Cl. You're saying, okay, how much of H2O, how much of it is by mass is oxygen, and how much of it is hydrogen? And so if you were to just look at your periodic table and you say, okay, well, how much mass does oxygen have? So oxygen has 15.999 grams per mole, and hydrogen has 1.008 grams per mole. So just logically thinking, you would think, okay, oxygen is way heavier than hydrogen. So I should have a higher percentage of oxygen for my percent composition than I do of hydrogen. And sure enough, when you actually do the math, you find, yeah, I totally do. I have oxygen makes up this 88.8% of H2O, and hydrogen makes up 11.2%. And Cl2, it's 100%, chlorine, because Cl2 is just chlorine bonded to itself, and there's nothing else for it to be bonded to. So this is just, I think, just a helpful image of a slide that's talking about exactly what we just talked about with percent composition. If you wanted to see the equation actually written out, it's just saying the percent composition equals the mass of that one element over the total molar mass of the whole compound. So all those elements in the compound's mass combined times 100, which will give you your percentage. So when you add A, B, and C's percent together, you should get a total of 100%. So this is going to be our practice problem, and I'm not going to do it on the board. I'm actually just going to do it here on the PowerPoint. So to determine the percentage composition of sodium carbonate. So the first thing we're going to do is find the molar mass of each element involved. So you have sodium, you have carbon, and you have oxygen. Now, you have to pay attention to these subscripts. The subscripts are telling you how much of that element is in that compound. So for this compound, you have 2 sodium, which they showed here. You have 2 sodium, you have 1 carbon. See, there's no subscript, so we just assume that's just 1. And you have 3 oxygen. So they wrote a 1 and they wrote a 3. And then they went and found the molar mass for each of those atoms, which again, you just find on your periodic table. So they found them up and then they did the sum total. So your molar mass of your entire sodium carbonate compound is 106 grams. So now that you know what the total is, you can actually find the percent compositions. So what you'll do is you take, sodium's solo molar mass, which is 46 grams, and you divide it by the total molar mass of sodium carbonate, and you multiply it by 100. And then you just do that for all of your varying atoms. And And sorry, sodium, I said solo sodium, but it's 2 sodiums. That's why they have 46 there. And you're doing it for all of your atoms, specifically an Na2CO3. And that'll give you all of your percents. So this is just like pretty straightforward. It doesn't require any converting or any additional steps. You just have to make sure that you're paying attention to these subscripts so that you don't just report a molar mass of just 1 sodium. Like in this compound, you have 2 sodiums, so you have to report for both of those. So your law of definite composition, I think, is actually a pretty cool law. So what it's saying is there's a ratio of elements in a compound is constant for every particle in that compound. So if you have 1 gram of CO2 and you have 16 grams of CO2, the percent composition of how much oxygen is in 1 gram of CO2 versus how much oxygen is in 16 grams of CO2, it literally doesn't change. Because you're talking about carbon bonded to 2 oxygens. That is never going to change. Like, that compound will always be carbon bonded to 2 oxygens, regardless of how much or how little you have. If you're talking about CO2, you will always have, 72.7% oxygen and 27.3% carbon. That is your masses that make up, or the percent composition of your masses that make up CO2. So hopefully that just kind of helps make sense that you don't have to multiply anything, because CO2 fundamentally never changed. You just added more of it or less of it, but the compound itself doesn't change. So for this practice problem, we already did one that focused on just finding your percent compositions. Now we're going to take it a step further and say, let's use our percent compositions to find our mass. And so this question is asking, how many grams of oxygen would a 65.00 gram sample of aluminum sulfate contain if you know that the percent composition of oxygen in a 30 gram sample of aluminum sulfate is 56.11%? That's just like a huge mouthful, and it sounds really confusing. So let's just break it down step by step. Always start with what you're looking for. What is our unknown? We want to find our grams of oxygen. That is our unknown. Next, we're going to write out all of our known. So we know that there is 65.00 grams of aluminum sulfate. That is the sample size we're working with at the moment. We also know that the percent composition of oxygen is 56.11%. Now, there's a third number given, and that's 30 grams a sample. This was the previous sample size, and that is how they calculated, this percentage of oxygen using that previous sample. And so the question is, do we need to do anything with that number, with that previous sample size? And the answer is no, which is great news because of the law of definite composition, meaning the oxygen in aluminum sulfate, we're never going to change how many oxygens are in aluminum sulfate. We might have lots of aluminum sulfate molecules, or we might have a little bit of aluminum sulfate molecules, but we're never going to actually switch out how much oxygen makes up aluminum sulfate. If we did that, that would just change the molecule. It would no longer be aluminum sulfate. It'd be something different. So, because we never actually changed the structure of the molecule itself, the law of definite composition states that that structure, each atom in that structure is going to contribute a certain amount of mass, and that mass is never going to change because we never changed the actual structure. And so regardless of your sample size, if you have 30 grams versus 65 grams versus 1,200 grams, oxygen will always make up 56.11% of the mass of aluminum sulfate. It just always will. So now that we've explained that, this problem setup is going to be just kind of different from all the other ones. We're not going to be canceling anything out, which is, kind of nice. But before we do that, we're going to need to convert this percentage back into a decimal, because you really can't just multiply by a percentage. So we divide by 100, and so we get 0.5611. All right, and so our equation is going to be our known, which is 65.00 grams of aluminum sulfate, and that is going to be times our 0.5611, and that is going to get us to, because this is specifically for oxygen, so it's saying what is the grams. If this is the percentage of oxygen and we multiply it by our sample size, that is going to give us, because this grams, it doesn't cancel out. We don't have any unit to cancel that grams out with. It's going to get us our oxygen. So once you pause the video and do the calculations yourself, the final answer is going to be, sorry, I have it written down over here, 36.47 grams of oxygen. So the cool thing about these is they're like pretty simple in terms of math, but probably a little more tricky in terms of figuring out like what exactly you're trying to do with your equation. So don't get confused by these extra numbers given. Just know like, okay, I know that this percentage is never going to change because of the law of definite composition. And then I can use that to solve for this particular sample size, the amount of grams that are in it. Cool. This is for calculating empirical formulas from percent compositions. And this is very practical in real life. If you are in a lab situation and you can figure out the percent compositions of an unknown compound, like like, okay, these are carbons, these are hydrogens, these are its percent compositions within this compound, but how many carbons are there, how many hydrogens are there, you can use the math to actually figure that out. So for doing this, we are going to take the first step. We're going to assume a 100-gram sample of the compound, if not told otherwise. So in a previous, thing about percent compositions, you were told, like, we're specifically focusing on this sample size. But in this, we're just giving you a percent composition, and we're saying, okay, assume 100 grams. So step 2 is you convert the percentages of each element to grams. So if you have 75% of something, that's 75 out of 100, is how you get your percentage, right? You multiply it by 100. So if you assume a 100-gram sample, then it's just going to be 75 grams. Like, it's just the exact same number, but with grams instead of a percent, because it's that 100-gram sample size. Number 3, you convert your grams to moles using your atomic masses. And so you would find out, like, okay, well, what is the mass of carbon? And then I'm going to end up, dividing 75 grams times its atomic mass or molar mass, and that will get me to 6.25 moles of carbon. Then you divide the moles of each element by the smallest number of moles to get the simplest whole number mole ratio. So 625 and 24.80, you would divide each number by the smallest mole, which is 6.25. So I divide that by 6.25, I divide this by 6.25, and I get a 1 over a 4. And the 4 was rounded slightly up to get to 4. And then you have your empirical formula of CH4. In the previous slide, I talked about how you would have to round that slightly up to get to your 4. It was very close to 4. It was 3.968 if you did the math, and that's why the 0.9, they were able to round up to a 4. However, when you're doing these problems, not all of them will actually give you this nice close number, enough to round. And so if that's the case, these are rules for figuring out how to, you don't actually round unless it's like a 0.01 or 0.99, like something very, very close. You would end up making it into a fraction and then multiplying by the denominator to then get your whole number. And you would do that to every single mole ratio that you found. This will make more sense as you do practice problems. This practice problem is going to go from knowing the mass compositions and from there figuring out the empirical formula. So our mass compositions, if you refer to this little flow chart, is going to be already in step 2. So we kind of skipped the percent composition. We went straight to knowing the mass compositions, assuming a 100-gram sample. And from there, we're going to go to our mole composition, and then mole ratio. Finally, it'll get us to our empirical formula. So aspirin is the common name for acetylsalicylic acid. If 100 grams of aspirin contains 60 grams of carbon, 4.480 grams of hydrogen, and 35.53 grams of oxygen, what is its empirical formula? This is a mouthful, and there's a lot of steps, but they're very simple, but you just can't rush it. You just kind of have to take your time going through it. So as always, we start out by writing our unknowns. So what are we trying to find? Make sure you can see this. We are trying to find the empirical formula. So what do we know? We are given the grams in this sample of carbon, hydrogen, and oxygen. So their mass composition is, 6 grams, 4.480 grams of hydrogen, 35.53 grams of oxygen makes up the mass of the compound. What we also know, looking up on our periodic table, is because we know we have to go from mass to moles, that means we need to know the molar mass to do the conversion. So for carbon, every 1 mole of carbon is 12.011 grams. For every 1 mole of hydrogen, it's 0.08 grams, and then oxygen is 15.99. Again, you just look on your periodic table, and these are the numbers written under your elements. So now that we have those, we can proceed to our second step of the flowchart, our first step for this problem. So we're going from mass to moles. So from grams to moles. So what do we need to do? Well, we need to, let's see, I've written out here. Trying to show you each step. There we go. All right, so I wrote out the mass that we're given, our known masses that we're given. So for carbon, it's 60. For hydrogen, it's 4.480, and then oxygen. And then I'm saying, okay, what I can do is convert each of these mass of the composition over to the moles. So how many moles is in that compound? Well, I do that by canceling out. Sorry, let's see if I can hold this real quick. We write it, so we cancel out our units. So grams and grams of carbon, grams of hydrogen, grams of hydrogen, grams of oxygen, grams of oxygen. So all those get canceled out, and it leaves us with our moles. So then we do the math. It's just 60 divided by 12.011, and then the same thing with the other ones. Sorry. And that will give us to our final answers. So hopefully you are pausing the video and doing the math, but if you're not, these are the final answers. So this gives you the moles. So you looked at our flowchart, so we now have our moles, okay? But we had to do another step. We need to figure out, okay, what are our mole ratios? So to figure that out is you take the smallest mole number and you divide every single mole by the smallest one in that compound. So 2.221 is the smallest mole for figuring out how many moles are in this compound. So let's see. Okay. So basically, I just wrote out the moles that we figured out from that previous step. So carbon had 4.995 moles, and I divided it by the smallest mole found, which was 2.221, which was, oxygen's mole. And I did that for each of them, and this is the answers I found: 2.25, 2, and 1. So these are our mole ratios, which is great. However, this is where the rounding question comes in. We cannot report these, we can't make a subscript for a compound a fraction or a decimal. Like, you just can't. You have to get it to its simplest whole number ratio. So 2.25, you do not round. We don't round these. We only round if it's like a 0.9 or like 0.1, 0.01. So what we are going to do is we're going to convert. Let's see if I can try to, I guess you'll just see it. You convert 2.25 to a fraction. So that's 9/4. And then you just multiply by the denominator to get rid of the fraction to make it into 9. So what you do to one of these mole ratio numbers, you have to do to all. So we have to multiply all these by 4. So that gets you 9 for carbon, 8 for hydrogen, 4 for oxygen. And then you write your empirical formula, meaning you have 9 carbons present, you have 8 hydrogen present, and you have 4 oxygen present. And that is how you go from having your mass all the way to your empirical formula. Now, if you had to start from your percent composition, you could totally do that. You would just convert over. So this would be, 60%, 4.480%, 35.53%, and then we assume 100 grams, and then we just 100 gram sample, and then we can just write it out like this. So it's like the exact same numbers. So it's not that it's necessarily complicated, but there are multiple steps, and you have to take your time to just write them all out. Stoichiometry means the calculation of reactants and products in the chemical reactions based on balanced equations. It's like, what? Stoichiometry, you're just looking at your coefficients in a balanced equation. So it's a mathematical relationship between how many reactants you have and how much products you have. And the reason why we can say that there is a relationship between those things is because you have conservation of mass. Like, if you have hydrogen and oxygen reacting together, hydrogen doesn't just disappear. Oxygen doesn't just disappear. They continue to be present. Hydrogen and oxygen, they might combine together in a different form, but there's still going to be the same amount of hydrogen and oxygen as you have on the left side. So that's talking about the balancing of equations. You have to have the same amount of mass on each side. Mole ratios. What mole ratios are is they are the coefficients in the balanced equation that will give you the moles of the reactants and products. So when you have this balanced equation right here, you say, 2 hydrogen gas plus oxygen gas yields water, 2 water. So these numbers right here, the number of molecules, you have a 2, there's a 1, there's a 2. Those are going to tell you, okay, there are 2 moles of H2, there's 1 mole of oxygen, and 2 moles of H2O. So this is just saying, like, you know how we just did that long practice problem, figuring out the empirical formula, figuring out the mole ratios? Well, if we have an actual equation already written out for us, we don't have to do a bunch of math to figure out the ratios. Those are the ratios, the coefficients next to the element or compound is the moles. And then from there we can find the ratio. So the ratio would be 2, 1, 2. It's like pretty nice that we don't have to do any math for that. So mole to mole conversion is you're going to have your moles, and then you're going to multiply by your mole ratio to get your desired number of moles. We will do a practice problem going from mole to mole conversion. And I think you guys are really going to like these. So how many moles of oxygen are produced by the decomposition of 6 moles of potassium chloride? So what we are going to do for these ones is we are going to first write out our equation. And if you have a paper, it'd be already there. But I wrote out the equation on the board, and I specifically did the coefficients in a different color because that's going to be important. Remember, the coefficients tell us how many moles of the compound or the element is in this equation. So we are going to do our unknown first, and that is our moles of O2. That is what we were trying to figure out. We're trying to figure out how much of moles of O2 is produced when we use the known 6 moles of potassium chloride. So another thing that we know, that I didn't write yet because I wanted to do it with you guys, is we know our mole ratio. So we're specifically looking at O2, so we can circle that, and potassium chlorate. We can circle this guy. So what is our mole ratio? Use a different color. So our mole ratio, we know that KClO3 is going to have 2 moles present, And O2 in this formula has 3 moles present. So now we can set up our equation. So we start with our known. We always start with the known, which is 6 moles of KClO3. And we are going to multiply this by our mole ratio. So our mole ratio, remember, we need to make sure our units cancel out, because we're not looking for moles of KClO3, we're looking for our moles of O2. So that means we know KClO3 goes on bottom, O2 is going to go on top, and these are going to be moles. So we look at our ratio and we say there's 2 KClO3 and there is 3 moles of oxygen, and then we just do the math. So 6 times 3 is going to be 18 over 2, and that is going to be 9. Cancel out our our units. So this would have been 9 moles of O2. 9 moles of O2 would be produced specifically in this equation. Mass to mole conversions, it is going to have slightly more steps, because you need to go, not from moles to moles, you need to convert from your mass to a mole, which we've been doing. And that is where you use your molar mass, because you're going from grams to moles, and you're saying for every 1 mole, it's this many grams of this compound or this element. That'll get you your moles, and then you're going to multiply by your mole ratio, which you get from your balanced equation, and that will get you your desired amount of moles. This practice problem is going to be mass to mole conversions. So if 15.0 grams of dinitrogen tetroxide was produced, how many moles of oxygen were required? So we're going to start out by writing our equation. You need to kind of write out your equation, because this balanced equation, the coefficients for your balanced equation are going to tell you your mole ratios, which you'll need. So we write out our unknown. Our unknown is, we're trying to figure out how many moles of oxygen would be required to produce the grams of dinitrogen tetroxide. So what we know is, we know that there is 15.0 grams of N2O4, and because we're in grams and we know that we need to go to moles, we need to convert using our molar mass of N2O4. So we use our periodic table to figure out what is our overall mass of N2O4. Well, it's 92.0 grams when you do the math with 2 nitrogen and 4 oxygen, and you add those together. And then you also know what are your molar ratio is, is the coefficients that you got from your equation. So how I figured these out is, I looked at my equation, I found oxygen and dinitrogen tetroxide, and I looked at these, specifically these coefficients in front, the number that's in front of the element or the compound. So I have 2 in front of O2, and there's like an invisible 1 in front of that. So my molar ratio is O2 has 2 and N2O4 has 1. So now I can set up my problem. And I just think it's just a great idea to just set up your problem using just your units before you add any numbers to it. So we start with what we know. So that is grams of N2O4. And we're going to set that up. Now we want to cancel out the grams of N2O4, because we're trying to get it to go over to moles. So this will be moles of N2. Let me write that over a little bit. Oh man. A little bit more over. Moles of N2O4 times, again, we're looking for moles of O2, so we want to cancel out the moles of N2O4. And on the top, we're trying to get to moles of O2. So now that we've set this up, if we were to go and say, okay, did I set that up correctly? I would just go and cross off my units. Grams of N2O4, grams of N2O4, moles of N2O4, moles of N2O4. And I'm left with moles of oxygen. So now we can actually write in our numbers. So the given number is 15.0 grams of N2O4 times the molar mass is 92.0 grams of N2O4 over, or 1 mole over that, because there's 92.0 grams per 1 mole of this compound. And then we multiply it by our molar ratio. So our molar ratio, the moles of O2 was 2, and the moles of N2O4 was 1. And then we just do our math on our handy-dandy calculator, which once you do the calculations on your calculator, it should get you to 0.326 moles of O2. Now, we will report the answer to 3 digits of accuracy, 3 significant figures, because you were given 3 significant figures as your first number. So you always report it with the lowest significant figures given, which was 3 in this case. Now, if you need to figure out a mass given, and you need to figure out an unknown mass, this is just showing you a flow chart of how you do those conversions, how you go from this known mass to moles. You multiply by the mole ratio, which is those balanced coefficient numbers in your equation, and then that gives you your moles, and then you multiply again by the molar mass for your compound you're trying to figure out. So it's a really just handy flow chart. This is going to show you all the conversions we just did as just kind of like a summary. It's all right there. We're going to talk about your limiting reactant. So a limiting reactant is a reactant that is used up first in a reaction, and this will determine the amount of product that is formed. And if you can think in the opposite, you can have an excess reactant, and that is a reactant that is not going to be used up first. So if you look at this example right here, we have hydrogen and we have oxygen, and that's going to yield us water. Now, if there's 4 hydrogen and there's 4 oxygen, the limiting reactant to get water is going to be hydrogen, because you need 2 hydrogen for every 1 oxygen to make a water molecule. So your limiting reactant would be that hydrogen, because that's going to get used up before we use up all of our oxygen. Your excess reactant would be oxygen, because if you look on this side, on your product side, you would still have oxygen without it having turned into your desired product, water. So mathematically, when we are determining the limiting reactant, we're going to follow these steps. We're going to write and balance our chemical equation, and then we're going to convert all the reactants to moles. Then we're going to calculate the theoretical yield of the product from each reactant, which is just kind of a fancy way to say we're going to use the mole ratio to say, like, if this reaction occurred, all the way through without any side reactions or any error, this is our theoretical yield. This is how much it should produce. And then we'll identify the limiting reactant from there. This is going to be just a practice problem for determining the limiting reactant and excess reactant. So, suppose we have a reaction where hydrogen gas reacts with nitrogen gas to produce ammonia. If we start with 10 grams of hydrogen and 15 grams of nitrogen, how do we determine which is the limiting reactant? So our first step was to write out our balanced equation. So we have N2 gas plus 3H2 gas yields 2NH3 gas. And it's important to make sure this is balanced, because these coefficients are going to be used for your mole ratios for calculating your final answer. So the next thing is you're going to convert all these grams that you were given over to moles. And so this is they just kind of like combined how we would normally write 10 grams times 1 mole over 2.02 grams of H2. That's just your molar mass of H2, from your periodic table times 2. And then this is the same thing with nitrogen. So they converted it over to moles, which is 4.95 moles and 0.54 moles. And then finally, you're going to take those moles and you're going to multiply it by your mole ratios. So you had 2 moles of NH3, which we saw in our balanced equation, 2 moles of NH3 right here. And I can even highlight, this is the coefficient that gives you that. So 2 moles of NH3 right here. And then maybe we can use a different color to highlight our 3 moles of H2 we got from this coefficient. And so they said, okay, for H2, you're going to have a total product of 3.30 moles of NH3. And then they did the exact same thing for N2, and it says your final product would be 1.08 moles of NH3. So the limiting reactant is the one that produces less product. So our limiting reactant is N2 because it produces less product than H2. So we would know if the question were to ask, okay, which one's the limiting reactant? You would say N2 is. And then which one is the excess reactant? It would be H2 because H2 has more product, meaning basically if you had more N2, H2 would keep going. It would take a longer time to run out of hydrogen before you run out of nitrogen. The percent yield, this is different from your percent composition, which we talked about earlier. So your percent yield is talking about the ratio of your actual yield that you get in lab over your theoretical yield that you calculate on your papers times 100. And so why the two are different is if you're like me, the probably biggest difference is you just made a ton of mistakes in lab and you were like very not precise, and you were like, good enough. And the reality is in chemistry, it's not good enough. You have to be very precise. So mistakes can be part of that contribution. But another contribution is that there's side reactions that are happening, and that is taking away some of those reactants that would be working towards making your product because it's reacting with something else. So there's just kind of a variety of reasons why your actual yield may be less than your theoretical yield because, it's real life and it's just kind of a little messy. But I think this is, just pretty straightforward in terms of figuring this out. And that, my friends, is the end of this lecture. So thanks for sticking with me.